Since the 1960s, there has been little progress in humanity's quest for the theory of everything. The two pillars of modern physics, quantum mechanics and general relativity, remain unreconciled. An important factor making the unification of these two theories more difficult is the mathematical fragmentation of the two. Quantum mechanics and general relativity have very different mathematical bases. Thus, communication between the two branches is made much more difficult. Moreover, to learn both quantum mechanics and general relativity, you need to learn a lot more math, so many people don't study both of them. Many similarities between the two theories may be made nearly impossible to find as well, further hindering unification. But why has physics become so mathematically fragmented anyway? I think one reason is that the tools we have been conventionally using were too weak, and so new theories required new systems that slowly grew until we reached the contemporary fragmentation. Indeed, I think one problem was the widespread adoption of Gibbs vectors towards the end of the 19th century, which, while being an ingenious formalism for vectors, was still too weak. Now, I should note that this isn't an accusation to the physicists of the 19th century. The most widely known alternative to Gibbs vectors at the time were the radically unintuitive quaternions by William Rowan Hamilton, so it is no surprise Gibbs vectors were chosen. Nonetheless, while physicists were arguing about whether to use quaternions or Gibbs vectors, perhaps they should have been asking a different question, one that Freeman Dyson asked much later himself. That is, how can it happen that the properties of three-dimensional space are represented equally well by two quite different and incompatible algebraic structures? Now, unbeknownst to Freeman Dyson, this question had already been answered by the time he asked this by a man called William Kingdon Clifford. He united both quaternions and Gibbs vectors in geometric algebra and explained also why they are so different yet work as well. Geometric algebra also turned out to be a very useful language for other things as well. For example, both quantum mechanics and general relativity can be done in geometric algebra, which means it is a potential language in which the two could finally be unified for a theory of everything. But even if that is still too ambitious a goal, it will at least aid communication between the disciplines. So I'll get now to the index, or what we're going to talk about in this video. In my Matura-Arbeit, I discuss special relativity as well. We won't be doing that due to time constraints and making this palatable for an audience, so we won't be discussing the inner product, complex numbers and quaternions, and also special relativity and Dirac matrices, which means we are left over with this 5-point program, which is what we will discuss. So we'll begin with the outer product. The outer product of two vectors looks a bit like this. You have two vectors A and B, as you can see, and the outer product A wedge B, as you can see here, represents the oriented area between them. Now you heard me say oriented area. What does that mean? Well, look at, for example, a piece of paper. A piece of paper has, in two dimensions, either a front-facing orientation or a back-facing orientation. Something like this, for example. Because these oriented areas are oriented, A wedge B is minus B wedge A, because they have an opposite orientation. So we would say it's adzi-commutes, which is a bit reminiscent of the cross product, perhaps, which the outer product actually replaces. The outer product has further properties. These oriented areas, these bivectors as we call it, can be added to each other, reminiscent of vector addition. Recall that vector addition looks a bit like this. You have two vectors A and B. You add them to each other by putting them at each ends, and then you get A plus B is equal to C, as you can see here. Now it's very similar with bivectors. If you have two bivectors, there's a green one here, there's a red one here. To add them, you just put them at each other's ends, as so. Make A plus B is equal to C, and C is this bivector of this oriented area between them. Great, and there was actually a mathematical rule hiding behind this animation. As you can see here, those oriented areas we saw were A wedge B and A wedge C, and you can see that A wedge B plus A wedge C is A wedge B plus C, and so we get the distributive property. This may seem like a normal thing, but you actually have to show this, but it's a very useful property in any case. Then we'll look at some other properties. If A and B are parallel, they do not span an area, as you can see. And because A wedge B encodes this area, it must be 0 then, which is in fact true. Yeah, there's another thing I want to know about bivectors or oriented areas, and that's that they only have a size and an orientation. They do not have a shape. So all these bivectors you're seeing right now are all the same bivector. They just have a different shape. But this shape doesn't actually matter. It's not encoded in the mathematics, and this is actually important and very useful because it lets us encode a lot of different things in bivectors. Great. So at this point, you may notice that we have zero-dimensional scalars, which is just normal real numbers, one-dimensional vectors, and two-dimensional bivectors. Now you may wonder, okay, can this continue on? Can we make three-dimensional objects, something like a trivector perhaps? And indeed, we can. This is a three-dimensional trivector here, and it's represented by A, wedge B, wedge C. And you can continue this on forever and make n-dimensional objects. At this point, I also want to talk about multivectors. We will use this mostly to generalize theorems for bigger objects. But a multivector is simply the addition of all these objects up to now. So scalar, vector, bivector, trivector, etc., etc. Now this addition may seem weird, but it's a bit like adding an apple to a pear in your snack box. You're not suddenly getting two pears. You still have an apple and a pear, just next to each other. This is similar. This also happens in math, for example, in complex numbers. You're not merging the imaginary unit with real numbers. Now, the careful viewer may have noticed that the dot product of two vectors, which of course have dimension 1, is a zero-dimensional object, a scalar, and thus lowers the dimension, while the outer product of two vectors A, which B, gives a kind of two-dimensional object and raises the dimension. And geometric algebra actually uses this. So what happens is, to use the best of both worlds, we just simply add them. Now, this is used in geometric algebra. In the geometric product, you define AB is simply the addition of the dot product plus a outer product B. And this is called the fundamental identity and defines the geometric product. There's also some other properties, but those aren't very important, and those are in the paper. Perfect. So let's figure out, okay, this is a weird definition. We're adding a scalar to a bivector. What else? What can we do with this? Well, we'll prove some theorems and then do some fun stuff with it. First, if two vectors A and B are parallel, then AB is BA if the vectors commute. This at first may seem weird. Doesn't every product commute? This isn't true. If you look at matrices, they don't commute. You don't have AB's BA, and the same is true in geometric algebra. But in this case, it is true. So we'll prove that. So we have AB is A dot B plus A wedge B. Now, recall from the picture on the left that A wedge B is 0. There's no area there, so just A dot B. A dot B is, of course, B dot A, if you recall high school. And then this is equal to B dot A plus B wedge A, because B wedge A is also 0. It also has no area. And you may see that the fundamental identity is in here again, so this is just equal to BA. Great, then I will show some other theorems that really show, again, that this is a geometric product. For example, if vectors AB are orthogonal, which means perpendicular, then AB is minus BA if vectors anticommute. So I'm not going to prove this. It's an analogous proof as before, but this is very important. You can see here again this lack of necessarily commutativity playing out. Exactly, and there's corollary that you can prove from this if you have two different orthogonal basis vectors, that is, vectors with length 1, then they anticommute as well. So EI, EJ is equal to minus EJ, UI. And we will use this quite often later on. Okay, now that we've got some of the theorems done, we can get into reflections. On the right here, you can see a reflection graphically. We have a vector V being reflected across the red vector M to the ref. Now, the geometric algebra equation for this is displayed on top right in black, and we're going to prove that. So, right here, you can see the equation on the left, and what we're going to do is we're going to take V and decompose it into the parallel, which is the green vector, and the perpendicular, which is the gray vector. The parallel is, of course, parallel to M, the perpendicular, perpendicular. Now we use the distributive property to get this. Next, what we're going to do, and this is a very important step, M and V parallel are, of course, parallel, which means that according to the theorems we proved before, they commute, so we can change their order. Then in the second term, M, V perpendicular, M and V perpendicular are, of course, perpendicular, which means that we can change their order, but we need to add a negative sign. That's exactly what we do here. And at this point, you may notice that m times m inverse is equal to 1, and so we get this. Now, if you look up the graphic, you see that that is indeed vref. If you go along the green arrow and then to the left, that is what we get. Great. Now, this formula has nicer properties than the normal way of doing it, because using this formula, we then do rotations, because every rotation can be composed from two reflections. Here, for example, you have the vector v being reflected across n to vref, and then across n to vrot. And this then gives you a rotation by theta. Now, I won't get into the details of how we turn this into a rotation, because you have to change some constants here and there. So I'll just give you results for now. Normally, when we want to do a rotation, we choose an axis of rotation around which we want to rotate and an angle by which we rotate. However, this doesn't generalize very well. Axes of rotations are very three-dimensional phenomenon. They don't work that well in 2 dimensions. And in dimensions higher than 3, they don't work at all, which means that it's, for example, not useful in special relativity or general relativity, which operate in higher dimensional spaces. A better, more generalizable idea is the plane of rotation. So you choose a plane, B, in which you rotate, and an angle, and then you can do a rotation, and this goes for infinitely many dimensions. Great, and this plane B, this plane of rotation will be encoded in a bivector. Next, to do our rotation, we define an object that is called a rotor, R, which is cosine theta divided by 2 minus b sine theta divided by 2. So you have your scalar and a bivector or oriented area afterwards. Now the formula to rotate a vector v is then RVR inverse, which is a very concise formula and is used very, very much. Great. Now that we're done with rotations, we can get into some fun stuff. Spinors. Spinors are very, very scary for most people, and rightly so. They are still very confusing. One of the most famous mathematicians with regards to spinors, Michael Atiyah, says that they are still not properly understood. However, Clifford algebra or geometric algebra makes the discussion of spinors much more manageable. So we had a rotor before. What is the definition of a spinor? A spinor psi is equal to c times r, and c here is just a random scalar, and r is for rotor. Now a rotor is normally normalized, which means it has a length of 1. So multiplying it by c means you give it a variable length. This doesn't make much sense. Why would you multiply a rotating element by a scalar? But we'll see in an animation how the difference plays out. So here we have a vector A, and we're going to rotate using our rotor identity here, as you can see. Next, we're going to do it instead with our spinor psi, and then you get this equation instead. And as we rotate, first we use, of course, the rotor identity, that's there on the left, but then there's also the c squared term, which means that we actually stretch our vector as well. So this means that doing this sandwich product, I suppose, using the spinor results in a rotation and then an extension, which means that from any vector you can get to any other vector, which we use in the Matura-Arbeit to prove that spinors turn negative in a 360-degree rotation. Having spoken of spinors now, we can get into quantum mechanics. Now, as I've said before, quantum mechanics is one of the pillars of modern theoretical physics. It is the study of the extremely small, like objects as electrons, etc. One especially important part of quantum mechanics is the study of spin, which is a very odd property that has to do with spinors, as the name would suggest. Normally, spin is done mathematically using the Pauli matrices, which you can see here. Sigma 1, sigma 2, and sigma 3 represent or are linked to the x, y, and z basis vectors, but the exact relation is a bit obscure. We also have an imaginary unit in the middle matrix, which further obfuscates any real geometric understanding. The Pauli matrices have some further properties, which you can see here on the left. They anti-commute with each other, and they square to the identity matrix. Now, if you don't properly understand matrix mathematics, that doesn't matter, because we can get by with geometric algebra. In fact, you may notice that this is exactly the same as the fact that basis vectors anti-commute with each other, as you can see here. Furthermore, all of these vectors also square to 1. Due to this, you can show actually that these two, that the polymatrices and three-dimensional geometric algebra are actually isomorphic. This may seem not extremely important, but these two systems have very different geometric interpretations. For example, sigma 1 times sigma 2, as you can see at the top left, does not necessarily imply that it is an area, while E1, E2 is definitely an oriented area or bivector. There's many other objects that suddenly get geometric interpretations. This matters especially for quantum mechanics, which has a lot of different philosophical interpretations, at least 15 or more. And so a geometric understanding of what is going on can not only help for philosophical reasons, but also can help us in research opportunities. So for example, David Hastings, who has rewritten large parts of quantum mechanics in geometric algebra, has since reproposed as you can see here, Schrödinger's Zitterbewegung as an interpretation for electron spin, but with a non-trivial twist. And there's many other research opportunities perhaps waiting to be made by using geometric algebra in quantum mechanics. Great, now then I'll get to some further hallmarks of geometric algebra that I can't talk about due to time reasons and also for the sanity of my listeners or readers. First of all, of course, special relativity and general relativity are incorporated. Then it also has incorporated electromagnetism. So here you see the four Maxwell equations. You do not need to understand these, of course. However, these have since been united into one Maxwell equation of this form in geometric algebra. Now, there's a historical note that I think is quite important here. The original Maxwell equations were written in quaternions, and there were more than 20 of them. Then Gibbs developed actually his Gibbs vectors to unify these Maxwell equations into these four equations. And due to this unification, Gibbs vectors were used over quaternions. And now, of course, this has been brought down even further using geometric algebra. To do this, a geometric calculus was developed, which is very powerful and generalizes the Green, Stokes, and Gauss theorems for calculus. Many other things have been done as well, but as it's still rather in its infancy, many of the developments are still waiting to be made. Thus, geometric algebra has been successfully applied in quantum mechanics, as we saw in this video, but also in general relativity, finally providing a mathematical bridge between the two theories, which will hopefully greatly enhance communication and transfer of knowledge between the two. We saw that it is more efficient than conventional formalisms and gives more insight into the geometry as well. Due to this increased insight in geometry, we discovered many new avenues for research which will further aid in the quest for unification. Thus, with such an abundance of unification and insight, perhaps we truly can announce we have found the language for the theory of everything.